Here's the fourth problem. Same exact instructions. The transformed function in this case is 1 minus quantity x plus 5 squared. So we can see that we're squaring things here. That immediately tells us our basic function was the squaring function, x squared. Listing the transformations. So again, while I write the word transformations, think about how many things happened to get us from F to G. Well, how many do we see? We have this 5 added to the x, so that's 1. Then we have this minus out front, and we have this 1 here. So again, we have 3 transformations. Kind of rule of thumb, we've been doing reflections first. So we have a reflection. What are we reflecting in? Right, so it's not sufficient to just say, oh, you have a reflection. You can reflect in anything your heart desires. You have to specify the axis of reflection. So the fact that this minus is on the outside means that this is an output transformation, so it's a reflection in the x-axis. The x-axis is the one that impacts the y-coordinate. Okay, so again, if we're working through the coordinate analysis as we go, we start with the arbitrary point xy, and then after the reflection in the x-axis, we end up at x comma negative y. Next, again, doesn't really matter which of the two shifts you do next, but let's just deal with this one on the outside since we're dealing with the outside. So that's going to be a shift up 1 unit. Okay, so again, you're coming off of having done your reflection. So you're at x comma negative y. And a shift up is not going to impact the x coordinates, but it will add 1 to every one of your y coordinates. So you're at negative y plus 1. And it's probably nicer to write that as 1 minus y, so that's what we'll do in the next step. But we do still have one more transformation, which is this plus 5 on the inside. And that's going to be a shift left, 5 units. So notice that anytime that I have a reflection, I specify in what. So it's not enough to just say reflect. Anytime I have a shift, I specify not only how many units, but which direction, right? So you can say vertical shift, but then you got to specify that it's up still. So it might be easiest to just say shift up, and you have a horizontal shift, but you got to specify that it's to the left. So we have a shift up and a shift left. Okay, so again, we're starting at having finished our shift up. So we're at x comma 1 minus y. The shift left will not impact our y coordinate, so that stays the same, but we subtract 5 from our x coordinate with the shift to the left. And that's it. We are done with our final transformation. So that is the final destination. So you started with a point on F, and then you wound your way over, and this is where you ended up. So we have already completed the coordinate analysis. And I generally find once you're comfortable with the idea of coordinate analysis, it's actually really handy to do before you do the graph. It's a great tool in graphing. Okay, as always, let's graph our axes. Okay, that's good. And then here's our x-axis. Always label your axes. And then we have our old familiar friend, the quadratic function. We've already done a problem with it. We've done many problems with it. So there it is. Just remember it goes up forever, so it doesn't ever stop. And it's your call how many points you want to label on it, but at least 3. I'm sure that your graphs can be much prettier than mine. It's actually harder to graph neatly using the tablet. I've always found that my graphs look better when I'm just using pen and paper, but maybe you disagree. Okay, so I'm using these 3 points. The shape's really familiar for me. I don't feel the need to use more points, but always, always judge for yourself. There's nothing wrong with using more points if you need more points. Okay, so here we go. Here's our coordinate analysis chart. So here are our points on the graph of f. Again, if you need more, use more. And then over here, we will plot our points on the graph of g. So remember, whatever x was on f, that morphs into x minus 5 with g. And whatever y was, that morphs into 1 minus y. Okay, here goes. So we're going to take -1 and plug it in for x. We're going to take 1 and plug it in for y. So that becomes -6, comma 0. 0, 0 becomes -5, comma 1. Oops. There. And then 1, 1 becomes -4, comma 0. All right, here we go. So -1, 1 is -6, 0. 1, 2, 3, 4, 5, 6. -6, 0 is there. Here is -5, 1. Here is -4, 0. So same exact shape. Like, really keep that in mind, that none of the transformations we have seen will actually morph you out of the shape you started with. Even once you introduce stretches and compressions, you still have the same shape. It might be a little narrower or a little wider, but it's the same fundamental shape. So if you're getting a totally different animal, something's up, right? It should still be a basic parabola. Okay, so there is the graph of f in blue, the graph of g in green, and we have gone through all of the steps in the problem. We've indicated the basic function, we've listed the transformations, we've performed the coordinate analysis, and we've sketched both graphs, and we've got at least 3 points on each graph. They're labeled on F. On G, I didn't label them, which you can if you want. I just was worried about making my graph look cluttered for you all. That's the 4th example. 4 more to go.